Welcome to this explainer. We hear it all the time. People will say, oh, there's a good chance of rain later, or it's highly unlikely I'm ever going to win the lottery. But what do those phrases actually mean? They're kind of vague, right? They leave a ton of room for interpretation. Well, today, our mission is to translate that fuzzy, everyday language of chance into precise, concrete mathematics. We're going to completely master the probability scale. It's a brilliant little system that literally takes guesswork and turns it into certainty.
But that sounds almost like a paradox, doesn't it? Think about it. How on earth do we accurately measure the unknown? We live in a world packed with unpredictable variables, from the weather to who wins the game on Sunday to simply rolling a pair of dice. But here's the thing, mathematics really doesn't like chaos. Probability is the specific mathematical tool we use to tame that chaos. It gives us a reliable, structured framework to evaluate how likely things are to actually happen. It lets us make rational decisions even when the future is totally unclear. And to pull that off, we need a scale.
Okay, let's dive into this. Every good scale needs a starting point, right? A solid foundation. In the world of probability, we confidently anchor the absolute bottom of our scale with the number 0. Now in math, a probability of 0 doesn't just mean something is super hard or rare or a long shot. No, it means it is categorically, completely impossible. Imagine trying to roll a 7 on a standard single six-sided die. You can roll all day, but it simply cannot happen. 0 represents the total void of possibility.
Now let's jump all the way over to the complete opposite extreme. If 0 is the impossible, then the number 1 represents events that are absolutely 100% certain to happen. No doubts, no variables left to chance, no what-ifs. For example, if today is Monday, the probability that tomorrow is Tuesday is exactly 1. It's a guaranteed outcome. In the language of math, 1 is the hard ceiling of our probability scale. You literally cannot have a probability greater than 1 because you can't be more certain than absolute certainty.
So there are our boundaries, 0 and 1. But let's be real, life mostly happens somewhere in between those extremes. Let's walk through the 5 key vocabulary words that map out this journey. We start at 0, which is impossible. Moving up just a tiny bit, we hit the territory of the unlikely. These are things that probably won't happen, but hey, they still could. Then, right dead in the absolute center, we have an even chance, where an event is just as likely to happen as it is not to happen. Past that midpoint, we reach likely, events we really expect to occur, even with a slight chance they might not. And finally, we hit absolute certainty at the number 1. These 5 steps give us the perfect vocabulary for the unknown.
Now, what's really fascinating is how we can seamlessly translate these words straight into numbers. Just look right at the middle row here. Notice how even chance, the fraction 1/2, and the decimal 0.5 are perfectly lined up. That's because they're literally just 3 different languages expressing the exact same concept, right in the dead middle of our scale. Being fluent in probability means you can switch between words, fractions, and decimals without missing a beat. So, an impossible event is 0. A certain event is 1, or 1 over 1, or 1.0, and that even chance, perfectly balanced at 0.5.
Let's put this to work with a real scenario from our source material. Imagine a student named Martin is playing a game, and the data tells us Martin's probability of winning this game is 0.3. Instantly, your brain should be mapping this number onto our scale. Where exactly does 0.3 sit? Well, it's definitely bigger than 0, but it's less than our 0.5 even chance midpoint. So, mapping this decimal directly tells us that Martin winning is unlikely. But this naturally leads us to a really important secondary question. If his chance of winning is 0.3, what is the probability of Martin not winning?
So, the crucial point is this. All the possible outcomes of an event absolutely must add up to a certain one. Think about it. You either win or you don't. There's literally no third option. Because those 2 possibilities combine to equal our absolute certainty of 1, we can just do some simple math. 1 minus Martin's 0.3 chance of winning leaves us with exactly 0.7. And checking back with our mental scale, 0.7 is greater than an even chance. So this tells us definitively that Martin's probability of not winning is likely. See? This is how probability lets us mathematically map out every single side of a situation.
And this brilliantly illustrates what happens when we move from abstract math into a physical, hands-on experiment. Let me introduce you to Sophia and Zara. They're 2 students from the source material who decided they wanted to see this probability scale in action. Rather than just guessing, they designed a real-world test. They were going to throw 2 dice, add the scores together, and they actually committed to rolling them 100 times just to see exactly where the outcomes would land on that 0 to 1 scale. But before throwing a single die, they made their predictions. And this is exactly where everyday guesswork clashes with theoretical probability. Sophia hypothesized 7 is the most likely total. Zara, completely disagreeing, confidently stated, nope, all totals are equally likely. Think about this for a second. When you roll 2 dice and add them, you can get anything from a 2 all the way up to a 12. Does every single number have the exact same chance of showing up? Who do you think is right here? Sophia backing the number 7, or Zara, who believes in a perfectly even playing field?
Well, let's look at the results. By physically throwing those dice 100 times and meticulously recording every single outcome in a data table, they calculated the experimental probability. And the data was totally clear. The number 7 was rolled way more frequently than a 2 or a 12. But why? Because there are simply more combinations of 2 dice that add up to 7. You've got a 3 and 4, a 5 and 2, a 6 and 1. But there is only one single way to roll a 2. Snake eyes, a 1 and a 1. By mapping those frequencies back to our 0 to 1 scale, they proved mathematically that rolling a 7 leans way closer to likely. Sophia's prediction was absolutely right. It proves that probability isn't just random luck. It's an underlying structural reality.
Which leaves us with a pretty fascinating thought to walk away with. If a precise understanding of probability can completely tame the chaos of rolling dice, revealing a hidden mathematical structure right inside a totally random throw, how much of your own unpredictable future can be mapped on a scale of 0 to 1? Honestly, every time you check a weather forecast, assess a risk, or just make a strategic choice, you are navigating this exact scale. Thank you so much for joining me on this explainer, tracing the journey from guesswork to absolute certainty. If this helped you master the probability scale, please like, share, and subscribe so we can keep decoding these fascinating topics together.